Hey, good morning. I'm sorry about the delay. I had some technical difficulties uh, getting this video online, but I think we're going to be good to go now. So for today, what we're going to talk about, we're going to introduce center of rotation and how it relates to center of gravity, which we learned about the last time we were in class. So what I want you to do for your do now is I want you to find the center of gravity of this object right here. Find the centroid. So both in the x direction and the y direction, find the center of gravity. And here's the formula as a reminder for center of gravity. So you take each of the individual weights and multiply them by their distances from a certain starting point, and add all those together and divide by the total weight of the entire object. In this shape here, every box is 1 inch by 1 inch. So you should use that as your guide for the size of this shape. So each box is 1 inch by 1 inch. So you should pause the video here. It should take you about 10 minutes and resume once you're done. So pause here. Okay. Now that you've completed that, let's go through this problem together. So for starters, the x direction. So you can actually plug in all of these weights and solve for x. But if you actually look closely at these numbers here, you'll see that there is symmetry across this object. There's symmetry. So the 0.2 pounds is on both sides here. The 0.2 pounds is on both sides here. The 0.75 pounds are on both sides here. All of these objects are smack in the middle of this object. So our center of gravity in the x direction is just going to be halfway along this object. So it's going to be here in the center. So if our starting point is right here, that distance would be 1, 2, 3, 4, 5, 6 inches. 6 inches or 6 inches, either way is fine. Okay, our center of gravity now, the y direction, the formula. And the distance, it's important that we note this, is going to be to the center of the mass, not to the end of the mass, but the center of the mass, because each of these weights have their center of gravity in the center of them. So the first, we're going to take these 4 objects. The first one, we'll do these 2.2s over here. So it's 0.2 pounds times 2 inches. Same thing over here, plus 0.2 times 2. We'll do the other 0.2, so that's 1, 2, 3, 4, 5, 6, 7, 8 inches over, plus 0.2 times 8, plus 0.2 times 8. Okay, so that's these 4 weights taken care of. Now we have these 2.75s, which are 1, 2, 3, 4, 5 inches in. So plus 0.75 times 5 plus 0.75 times 5. I could have, of course, just multiplied each of these by 2 instead of writing it out this way, but it doesn't really make a big difference. Now this 2.5 is 1 inch away, 1 inch up, plus 2.5 times 1. Then we have this 1 pound, which is 1, 2, 3, 3.5. So 1 times 3.5. Then we have these 2 pounds. It's 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6 inches up. And then the 1.5 is right here. So it's 1, 2, 3, 4, 5, 6, 7, 8, 9 inches up. I'm just going to check to make sure I have the right number of weights. So I'm just going to count here. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 10 weights. I should have 10 weights here. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Okay, great. And that's going to be divided by the entire weight. So that's 0.2 plus 0.2. Actually, I'm just going to write 4 times 0.2 plus 2 times 0.75, 4, 6, 7, 8, 9, 10, 10 weights. Perfect. So I'm just going to take my calculator. I'm going to plug this all in. And I get 43 divided by 9.3, which is equal to 4.62. I'll round it to the nearest hundredth. And this is going to be in inches because the denominator here is in pounds, and all of these units are going to be inch pounds. We're going to divide everything by pounds, and we're going to end up with inches. So 4.62 inches, that's about 1, 2, 3, 4.62. That's about right here. That's going to be our centroid, the intersection of our center of gravity in the x direction and our center of gravity in the y direction. Now, you might have realized that this free body diagram I have set up here looks a lot like the robots that you guys built. It's got 4 of these, which look a lot like wheels. It's got a tower and an arm and a claw, 2 motors, a battery. I know I've left out a few details, but this is just to kind of represent what your robots look like. Now, the reason I did this is today we're going to talk about center of rotation. What that means is when you have a tank drive, it rotates about a point. And this point is known as their center of rotation. So for your clawbots, when they turned in place, they were turning about their center of rotation. If you have 4 wheels that are all the same, and you have a tank drive, your center of rotation is going to be the same as your center of gravity. So again, if all 4 wheels are the same, and the thing that's the same about them specifically is their coefficient of friction, if all 4 wheels are the same, the center of rotation is the same as the center of gravity or centroid. Okay. Now, let's talk about why this is, and then jump into what if they're not the same, what happens, and why would you potentially want them to not be the same. So let's say you have your drive base. Here's a drive base. And it's got 4 wheels. When you turn in place, when you drive this side, the left side, up, and the right side down, what happens is the wheels, the robot is actually fighting the frictional force that's being generated by the wheels, so because there's a friction, a sideways friction. If I put my robot on the ground and I try to push it sideways, I get a friction force that resists. That same friction force is what's stopping you from turning. So as you're turning these wheels this way and these wheels this way, we get a vector of force that's going this way, and we're getting a vector of resistance provided by the friction that goes that way. This wheel, you're turning this way, and the resistance goes in the opposite direction. Same thing down here. And the same thing down here. Because the force, these black arrows, are greater than the blue arrows, you're able to turn. If your friction is, so great that you can't overcome it, well then, those blue arrows will be greater and you won't move. But so this is referred to as scrub. So this thing that you fight as you turn is called scrub. And you want the scrub to be, sometimes you want it to be great because the greater it is, the harder it is to for another robot to push you sideways or to push you around. But you don't want it to be so great that you can't turn because this will generate torque and it'll stall your motors if you're not careful. Now the way we calculate this torque is we go back to frictional force. So if you recall, the formula for frictional force is mu times our normal force. So each of these wheels has a normal force applied to them because all your weight is put onto the ground through these four wheels. So the way you can think about it is you have this normal force that's acting at a distance, depending on where your center of gravity is. But that normal force is evenly distributed amongst the four wheels. So at each wheel, the normal force is total normal force divided by the number of wheels, which in this case would be four wheels. So if we were to look at this, we had our centroid and the last one close to the middle. Let's put it right in the middle of this object. Let's say that our center of gravity is right in the middle. 1, 2, 3, 4, 5, 6, 7. Oops, made an odd number, so it's a little funky. It's okay. Let's say our center of gravity is right here. When we turn in this direction, like I have laid out with these vectors, we turn in this direction, we get a lever effect on each side. So it's as if there is a lever right here. There's a distance, we'll call it D1, and a frictional force that we're fighting against. We'll call it frictional force 1. That's resisting our turning. And the same thing happens at the bottom. There's a distance, call it distance 2, and a frictional force that's resisting our turning, call it frictional force 2. So when you turn, we have two torques. We have torque 1 is going to be equal to frictional force 1 times D1. And we have torque 2 is equal to frictional force 2 times D2. The two torques have to be equal. And this point here actually isn't our centroid, it's our center of rotation. So as these frictional forces change, this point is going to move towards one side of the robot or the other, depending on what that frictional force is. Now, what can change about our frictional force? Generally, we could change two things. We could change our normal force or our coefficient of friction. So we can change where our center of gravity is, or we can change what our coefficient of friction is. In the first example, we assumed all the coefficient of frictions were the same. And here, if all the coefficient of frictions are the same, you're just going to turn about your center of rotation. But the thing to note is frictional force 1, go back to blue. Frictional force 1 is going to be equal to mu1 times normal force on that wheel. So in this case, it's be normal force divided by 4. And frictional force 2 is going to be equal to mu2 times normal force over 4. So basically what this is saying is if mu1 is greater than mu2, mu1 being the friction, the coefficient of friction of the wheels up top. If the coefficient of friction of the wheels up top is greater than the coefficient of friction of the wheels down low, then distance 1 is going to be less than distance 2. The center of rotation is going to, if the coefficient of friction is greater up front, is going to shift towards the front wheels. It's going to shift towards the front wheels, and you'll tend to turn about the front wheels as opposed to the back wheels. And the reverse is true. If coefficient of friction 2 is greater than coefficient of friction 1, then D2 is going to be less than D1. At this point, you might be asking, okay, well, what if these two are different? Well, that actually complicates things, but you wouldn't do that on a robot because that's going to cause this center of rotation to not only move forward and back, but it's actually going to move side to side. And it's really hard to control a robot that has a center of rotation that's off to one side and not close to your center horizontally. It becomes really difficult to control, and there are no real applications for that. I mean, I'm sure there's some, but I've never seen one. And you generally don't want to design or build for something like that. Okay, so I want to go back a second to the do now, and I want to, let's change things a little bit, and let's look at it. If mu1 is equal to 0.3 for this, and mu2 like a Pokemon, is equal to 0.05, let's try to find the center of rotation. So again, let's pause here. So let's try to find the center of rotation. Let's pause here and try it out. Try to find it on your own before we go through it together. And then we'll go through it together. So pause here. Take like 10 minutes. Okay, together. So pause here. Take like 10 minutes. Okay. To our frictional force 1 times our distance 1. We're not going to know distance 1 or distance 2. We need to solve for those. And torque 2 is going to be equal to force of friction 2 times distance 2. Okay. So torque 1 is going to be equal to 0.3 times our normal force. So it's going to be a quarter of our weight. Our total weight was 9.3, so it's going to be 9.3 divided by 4 times, and torque 2 is going to be equal, like I said before, torque 1 has to be equal to torque 2. So we set these two equal to each other. 0.3 times 9.3 over 4 times D1 is equal to 0.05 times 9.3 over 4 times D2. We can, and then you ask yourself, okay, now what? Because I don't know what either of these D1 or D2 are. But actually, we kind of do know something about them. If we look back at the do now, we don't know where our center of rotation is going to be. We know where our centroid is, but we don't know where our center of rotation is going to be. But we do know of the wheels. This distance is going to be equal to D1 plus D2. Because no matter where this point is, D1 and D2 are still going to add up to be the same thing. Whether it's here, or even here, and one of them is negative, it's still going to add up to the same thing. So that's going to be 1, 2, 3, 4, 5, 6 inches. 6 equals D1 plus D2. All right, so now we can go back here. So D1 plus D2 equals 6. We can say D1 equals 6 minus D2. Now we're just on to basic algebra. We plug this into here. 0.3 times 6 minus D2 equals 0.05 times d2. We can divide both sides by 0.3. 0.05 divided by 0.3. 6 minus d2 equals 0.172. Add d2 to both sides, so add 1. So you get 1.17 d2 equals 6. Then we do 6 divided by that. It's going to be equal, d2 is equal to 5.14. And then to find d1, d1 equals 6 minus 5.14. d1 equals just do that. A little sloppy, but that's okay. So that means that our center of rotation is going to be really close to these back wheels. These wheels up here, because we said this was mu1 and this was mu2. So our center of rotation is going to be 0.86 inches away from here. So it's going to be somewhere around here. That's going to be our center of rotation. Now the effect of this is, you'll just turn over closer to here, no problem. This is kind of simulating if you put omni wheels in the back of your robot, you would turn about here. Now, if a lot of your weight is far away from here, let's say your center of gravity is further away from your center of rotation, what's going to happen is it's going to take more torque to turn, and you're going to be more likely to stall your motors. So in general, you actually want to keep your center of gravity close to your center of rotation. You want to keep these two close together because that's going to really impact how much power your motors take when you turn. Okay, but that's not really important for today. Today we're just solving for this center of rotation and the center of gravity. But in general, we're these 2 points really close together. All right. So here's the math one more time, so you can pause it here and review it. Now for homework, I've created this additional diagram, and here is, again, it's 1 inch per square on my paper. You have these 4 wheels that are 0.2 pounds each. We have a 5-pound mass up front, a 1-pound mass over here. Let me focus this a little bit for you guys. To define the centroid, or the center of gravity, and the center of rotation of this robot using what we learned today. Please post any questions that you have. Our next video will be probably on Wednesday, but I'll be available for Google Classroom. If you have any questions, please ask on there because someone else might have the same question as you. Okay, until next time.